some new faces.
New faces.
He's talking to you.
He's even talking about math.
Lots of people like show up for the exam. It's really fun. It's nice to see. It wasn't like passive aggressive at all. I promise.
You like pointing out making more
Let's hold off on, excuse me, any homework questions until the review. We need to make sure we finish 11.3 and 11.4. We did start 11.3. So here's where we can compare, like, you know, what is this series? Does it represent a function? This is how we can construct these Taylor or Maclaurin series. And we did that for e to the x. So as a reminder, the coefficients here are the first derivative evaluated at the center times x minus the center to the same power as the derivative, which is there divided by the same factorial. Okay, and those gave us our Taylor polynomials. For e to the x, we found we just found the first few non-zero terms, looking at the function, its derivatives, and then evaluating those at the center, a equals 0, and then constructing our Taylor polynomial. It's a Maclaurin series because it's centered at 0. But we came up with the following series, x to the k over k factorial. We know that represents the function e to the x, but for what values of e to the x does that actually represent? We said then we've got to default now to methods from 11.2 and test for the interval of convergence. We use the ratio test, and we said that the ratio came out to be the absolute value of x times 0, and for convergence had to be less than 1. That is always less than 1, and so we said for any value of x will result in a convergent series, meaning we didn't get a chance to write down. This means e to the x does equal the sum from k equals 0 to infinity of x to the k over k factorial for all x. That is the interval of convergence is all real numbers, and the radius is so if you've looked ahead, you've seen a formula or a table of some Maclaurin series for e, sine, cosine, natural log, inverse tangent. All of those are derived the very same way.
So what are you supposed to change the value? There's some question where has you changed the value from 0 to 1?
I don't know specifically. All I can comment is like if you had this series that was like let's say it was like x to the k plus 1 over k plus 1, like to write that more compactly, I suppose, as x to the k over k, we would subtract 1. So let's say this is going from 0 to infinity. To write it more compactly, we would subtract 1 from the summand, and we would add 1 to the index. So this thing is this thing. Really, I think it's just a matter of neatness. If you wrote this series or this series, either one is correct. They're both the same.
But there's not going to be problems that you cannot solve it unless you change that index in the correct form to satisfy.
No, some of the so there were some homework questions where it was helpful to like shift the index to look at it as a p series.
Okay.
You know, like when we had the sum from like k equals 2 to infinity 1 over k minus 2. How should we do this? Subtract 2. Add 2. You know, something like that to the third. I don't know. When we looked at it like the sum from 1 over k cubed and we changed this index here, then it was a little bit more obvious that that was a p-series. But in a situation like either one of these, it's really not necessary to do that, although by convention it is usually done, just so it's neat. So that's our series for e to the x converges for all values of x. And again, notice when we plot this, let's go ahead and look at this. I think it's worthwhile to look at. Let's just maybe go out to terms. Okay, so there's the linear approximation of e to the x centered at 0. And then when we start adding more and more terms of that polynomial, see if the computer will catch that. It doesn't do such a good job. Here, we'll ignore that. But notice, like this is 100th degree Taylor polynomial. And note what we're saying here. We're saying that e to the x is this infinite sum. So as soon as that's not infinity, then it's a mere approximation. It's a really good approximation if we go out to 100 terms or whatever, but we're saying it's exact only as we go out to infinity. So that's exact e to the x. Again, when we look at that 100th degree polynomial, we can start to see the error or the difference. May not be for this one, but yeah. So we can see the difference. Where'd it go? Here, I'm gonna pull this back. It's having a hard time. Okay, 38. So let's see this. We have to get super close, but so we start to see the difference between the actual function and that finite series, right? Here's e to the x. Here's the 38th degree Taylor polynomial, right? And we see that those differences are very, very small. Yet we see that it's not exact. They don't match up perfectly. It's only that these sums out to infinity are giving us the exact function. Does that make sense? All right, so y'all try this one. Maclaurin series. Remember, Maclaurin series means that the center A is equal to 0 for ln of 1 plus x. And maybe just try to get through part A and B for now. We'll see how that goes.
And like your first turn, technically you have to be 0 turns.
By the way, don't use the tables that are forthcoming. Don't cheat.
Do we have to memorize all those tables
It's not
on
really
Thursday?
You know, the ones on the tables, it's up to you if you want to memorize. I think it's exponentially more efficient to have those known as opposed to having to go through this process every single time. You want to know the series representation for a pretty common.
So between now and Thursday, memorize this paper shit. Have you seen it, Vic?
Yeah, so like
All your tests. All the conditions. Sometimes
It's really depending on the coefficient. Oh, yes. Yes. That's where roots.
yeah, this whole first page here is why is it scary? Like when you're trying to like simplify something,
Oh, yeah. Or be 1+X is 0.
He's doing it.
Just add 2 hours.
I know. Yeah, and I have to look, this is why I took it out. You gotta look at each term. It's for me, like reverse engineering all this phrase here into that is so
Yeah.
so like for example, I know all of these are means something. Sometimes if the term at the top is in this for example, I don't understand first term.
That's right.
It starts at 1.
Just as I finished that project.
Oh,
It took me like 7 tries.
What if one of my
I don't wanna hear it. I don't wanna hear it. I wanna think about, no, I wanna think about this, right? This is what can I do?
Yeah, I'd rather.
I don't know how.
1+X. That's not bad. That's
okay, yeah, well, that's honestly, I'm not.
And then the biggest thing was like investing it. I just feel like that one Spanish presentation last semester.
Yeah.
It was awesome. I was like, hey, this is a great opportunity to show our listeners and cats who did not get to see them. So I talked about my cats and then I went through the slides.
No, because it's only. Oh, no.
The sequel to yeah, so this would be.
Just test you full.
But I
Like a nightmare.
no, it was traumatizing. It took me a while to like get him.
Is that one of those? I was gonna say. Anytime I was young, I'd take that.
Yeah. Like measure where all the stuff is supposed to go. It is.
So that was just fair.
Except for the first one.
Almost never. Like according to my Fitbit, it tells you when you're in rest. Well, it thinks that it does. I'm actually awake a lot of the time. I'm
Except for, I don't know why, that's when we first started taking. I got one over.
So then for C,
So we're.
I guess I'm still not getting more.
Yeah, because like you're saying at 8, you're zero F.
Yeah. Tonight it's like 11 to 11.
Zero, you got one.
So.
I'm gonna bring it up. Yeah, well,
Can we make it dark, please? Can we dark this one?
Oh, we're in different part. I just can't. Oh,
Not all of them, just missing a tank. Negative goes right. Yeah, did you?
What'd you get for yourself?
the negative one.
You got nothing invested.
I mean, I pulled up.
Oh, yeah, because there's pluses and minuses in there, huh?
Yeah.
No, so each one, like, if you have it here, like, this is
And this doesn't even seem right to me.
weird, because your first term is gonna be zero for the first one.
Can I ask you a question? Yeah. So I did that, but can you explain to me why?
Yeah, and so here you should, I see where you're losing about So,
Yeah.
I mean, I'm
yeah, so you wouldn't.
Have you heard of cases?
That's, I mean, honestly, maybe that's the clearest pattern. I can usually, all right, well, if I sum this up, let's say for this, I can't start this. So, first term is x for 1, x to the 2 over 2, okay, that's good. We can take care of the k part, and we just have our negative 1. So you have to do k is 1, first term is a negative.
Which would be.
So now I always get x to the q. So I get start off with a positive, and then the next one is negative, positive.
natural log of 1.
Yeah.
Because of the important
Although I was considering, like, if I don't get myself how to manage episode, that lasts for the next 3 weeks, I
Then I
might
get zero.
some shit down. But that's
And where I was probably.
that's really insane. Like, if I could just get through the end of the semester and not like deal with my crazy kids shit afterwards.
Yeah, it's absolute value there. Because if we're testing for a solution, so that. Yeah.
So then what?
So I assume that I'm gonna do the ratio.
And then I take the limit of what?
So we wrote it.
Yeah, all of them.
I wish you would tell me. I like. What is chapter 12 about? Is it better than this?
Chapter 12 is the one where you see.
Yeah.
Oh, is it you're asking to get through that? Or no, I'm just chapter 12 in here, like there was something in there that looked like the, there's a horse on a bicycle wheel, and if you can just follow that point, it goes like that. It's kind of-
Flint Farm, she lives in Flint Farm.
Okay,
I'm taking it fast.
I just wrote it.
This thing right here.
No, because if it was negative 1 to the
So
10,
for F.
yeah, what you would just sit on cake completely.
Well, we're not smart. That's true, but like.
But I'm pretty sure we.
Right.
I'm excited about recount.
Yeah.
Which was bad enough at the time.
Actually.
And I think that that is probably what now, and I was really bad enough at the time.
That's traditional.
So we're evaluating it at 0. And so I can plug in.
That's just what we're gonna.
Well, I'm evaluating the section 0. Why am I not evaluating it?
Because those are right, because
So evaluating it first before plugging it.
yeah, this is actually one of the function X. So you have to have.
Right, so you guys get, and then, oh yeah, so here,
I just remember
which, yeah, has the first term doesn't have anything else.
Or now you can.
Yeah, so last time we already have to do it just like we have to do all of it tomorrow. Oh, yeah.
I think what's confusing is that when we find the derivative, we say it's not the drugs. But then we want to evaluate this, we want to evaluate that.
What is the X?
It's telling us to evaluate that. So, yeah. This is gonna give us this count. And that's gonna go into this number.
I knew one kid who did someone's test form for
Yeah,
like.
but that's your second one.
Apparently I did, yeah.
I'd love to be able to answer my shot.
No.
We all take part, kind of look at this.
So, okay, then I evaluated this continuous broke it up. Oh, I'm sorry.
I got a negative.
But what if you're solving?
This is correct, right?
Yeah, so you have to take something. If he
Oh, yeah. But that's not.
listen, if he goes up there,
So you
I'll make both you look at it. If I get this ratio root thing right, if he goes up there and
Yeah,
does
so
that.
what I came up with is because you have to
Look my dick up.
Yeah.
I do that right here.
Look at
I want to simplify it. This part right here is.
Because like.
Yeah, it's just,
So this should be X to the K.
so,
Which I have right now.
Where's the two coming from?
K to the X.
That's what this is. I don't know if that makes sense.
Well, yeah, so one to the K times one squared.
You guys have plus, squared.
Yeah.
Well, but does it, for the record? I can also over K plus one.
Yeah, so. Yeah, so basically these are formula.
Like springs out.
Yeah.
There's a video that went like really popular. I think it was a guy that it was like,
But that doesn't
like
help
a
anyone.
No, so that's, this is hard. I want to, what happens.
Oh, bring it outside.
Well, actually, this should.
Because it's X, right? Is it because it's X? Okay.
So then that would be one. And it's like one.
Not good. Would you continue on to do ratio or test? What did I say? They're all making fun of me, like, oh, you're stupid. Oh, yeah? I don't know how to do it.
I still need a petition for team.
Listen, you know what's tough? It's tough. It takes a minute. You're like, I would. You can get mad at me if you give me new ideas. Wait, so what is it? Benchmark?
Yeah, I didn't like this. Yeah.
I should watch this video. That one's hot. Oh, from.
But since the limit is one, since the limit is. It's inconclusive. Ratio is not out. If the ratio is one, it's inconclusive.
I don't know if you write it out like this, but the reason I'm going to evaluate the function at a, so the function and all of its derivatives get evaluated at the center. I think there was some confusion with the a's and the x's when to plug in a equals 0 versus x equals to 0. But you just got to remember this format here. You always evaluate the function and the derivatives at 0. So this f of x becomes f of a. If you want to look at it like this, this becomes f of a equals 1, or sorry, the ln of 1 plus a, where a is 0. Same thing for the first derivative. The first derivative at a is 1 plus a, sorry, to the negative 1, and so on and so on. And then we're plugging in a equals 0 into that. Does that make sense? Okay. Hopefully I didn't. My notation and confusing. So most of you are past this, which is fine. You can keep working. I'm just going to try to catch up since it's been about 30 minutes. Okay, so we find the function, its derivatives, and then we evaluate those derivatives at a equals to 0. And really, this is all we're after. Out of all of that, the whole purpose of taking the derivatives and then evaluating it at a was to get those numbers right there. Because those numbers are these numbers. That's all we've got so far. But the rest of it is a pattern, and it's always consistent. So from here we say the ln of 1 plus x, and then we construct our f of a. So if you want to write that, there's really no need, but the first term is 0. Then we have plus 1 times x to the first over 1 factorial. If you want to write out all of this according to the pattern, then our next term is what? Our coefficient. Next coefficient is negative 1, but this is coming from the second derivative, so this is going to be x minus 0 squared all over 2 factorial. Next coefficient was 2, coming from the third derivative. And then the fourth term, the fourth coefficient was negative 6, coming from the fourth derivative. It's an infinite sum. We're just going to stop at the first four. We were asked to find the first four. That allows us to see a pattern. So we're going to write this as a sum. And before we do that, I think it's easier to sort of simplify what you have, because we can fix the coefficients. 1 over 2 factorial is 1/2. 2 over 3 factorial is 2 over 6, which is 1/3. 6 over 24 is 1 over 4. So let's look at it that way before we actually write the series down. So it's much easier to work with, right? So if you can simplify, you should. It's simpler. Okay, so we're going to go from k equals something to infinity. Now, we didn't start off with the series, so it's up to us where we start the series, right? In previous exercises or sections, you know, it was like, hey, here's a telescoping series. Rewrite this, you know, or do something with the given series. We had to be mindful of where it was starting because it was already fixed or given to you that way. Here, there's nothing given to us other than the fact that we have this series, and I can choose to represent it any way I want to, as long as it fits these terms.
Right now, we just got rid of the coefficients.
Yeah, because this is 2 over 6, which is 1/3. This is 6 over 24, which is 1 over 4.
Okay.
Yeah. We see that the patterns fit the whatever expression, x to the k over k. And say, well, in order to get the first term as x to the first over 1, we would have to start at k equals to 1, right? So that gives us x to the first over 1, or x. The next term is a positive x squared over 2, positive x cubed over 3, positive, right? So now we come back and put in that alternation. We would say -1 to the, if we said -1 to the k, note the first term would be negative, our first term is positive. So we just say, let's start at -1 squared and make that a k plus 1. So here's part A, here's part B. Is everyone okay with that? All right, so then in part C, you actually have to now take this series and test it like we did in 11.2 with a root or a ratio to determine what's the interval of convergence. So then that's the next step. Did anyone get through this yet? Just curious. You did. Yeah, and then we have to test the endpoint. So did you get that far yet?
I got them done.
Okay. So we're going to test this series with the ratio. Limit as whatever we use, k goes to infinity. Remember, it's the absolute value because we got a variable x in there. If something converges absolutely, then it converges. So it's just much more convenient, especially also with alternating series. It's just much more convenient to start out this way. So we have the k plus 1 term. So we have x to the k plus 1 over k plus 1 times -1. Remember, k is now k plus 1, so it's k plus 1 plus 1, which is k plus 2. So there's a sub k plus 1. We're dividing that by a sub k, which means we're multiplying by its reciprocal. Since we're taking the absolute value, all of this alternation, -1 to the k plus 2, -1 to the k plus 1, that all just goes away. The only thing that we're required to keep an absolute value is anything dealing with x, because that's the thing that's varying. K is approaching infinity, so it's always positive. So we're taking the K over K plus 1 out of the absolute value, but we're still computing the limit on that. So it's the limit here. And so we've got x to the k over x to the k plus 1. That's like x cubed over x squared. You just end up with x, right? That's what we're dealing with as far as x goes. Is everyone okay with our simplification? Are there any questions on any of that?
The negative one go away, right?
Yeah, yeah. So we know that -1 to any power is either 1 or -1. And so when we take the absolute value of all of that stuff, the absolute value of 1 or -1 doesn't matter what it is. So remember, this is our ratio. This limit is equal to 1. We have the absolute value of x times 1, which just gives us the absolute value of x for the ratio of that series. Yeah.
How is the limit of k over k plus 1?
So that's a polynomial. We look at leading term over leading term, k divided by k. If you can't see these limits like that, there's no harm in applying L'Hopital's rule. So it's infinity over infinity. Derivative of k is 1. Derivative of k plus 1 is 1. Right? So you see that immediately with one application of L'Hopital's rule. Yeah.
So normally with the ratio test, if it comes out to 1, it's inconclusive. But
Right.
since we have x in here, does that kind of negate that rule?
Exactly.
Okay.
Yep. Yep. If that x weren't there, then this ratio test would be inconclusive. But we're saying that our ratio is the absolute value of x. And for convergence, that has to be less than 1. According to the ratio test. So we've got the absolute value of x has to be less than 1. And then that gives us the interval -1 to 1. Or -1 less than x less than positive 1. Okay, so that's where x has to be in order for that series we came up with to converge. Does anyone have any questions?
We need to check the.
Yeah, when you use the ratio test on these series, you have to check the endpoints. Because when x is -1, the absolute value of -1 is 1, and your ratio is 1. So there's inconclusive when r is equal to, or when x is equal to +1, again, that's 1, and the ratio is inconclusive when it's equal to 1.
Use the summation.
Yeah. So you're going to see what happens when I plug in x equal to -1 and x equal to 1 in that series I got in part B. What series results? So we're testing the endpoints in the series. Found in part B. Yeah, and so this could come up, you come up with a brand new series, but these series are of the flavor of chapter 10, where there is no variable in it. So then when we test these endpoints with this test, we always default back to a previous test. Is it geometric? Is it telescoping? Is it alternating series, etc.? Is it a P series? So when x equals to -1, the series that we had, which is -1 to the k plus 1, times x to the k over k, this becomes -1. then we have to ask ourselves, what does that particular series do? Does that series converge or does it diverge? Yeah, let's see if it is an alternating series. So we have, let's look at the -1 to the k times -1 times our -1 to the k all over k. So the -1 to the k times -1 to the k, we can put those -1s under the k, right? So it's just -1 times -1 all to the k. It's +1 to the k. 1 to the k is always 1, right? This k is 1, 2, 3, 4. It's 1 to the first, 1 to the second, 1 to the third, 1 to the fourth.
I'm sorry, Cody, can you explain that algebraic property there?
Yeah, so I'll write it out. We're going to take these two, this one and this one, and we're going to write it out like this.
That's like, you can do that. That's
Yeah, right. So like if I had, I don't know, like whatever that is, forget that. If I had 2 times x squared, I know that to be 4x squared, right?
Right.
Yeah. So it's the same.
I
It's the
got
same
you.
idea. We're just kind of working backwards. This is 2 squared times x squared. We're just going to rewrite it like that.
Gotcha.
Okay, and then we still have our -1. So there's really nothing we can do. That's just a -1 all over k. But this stuff in green is just 1 to the k, which is always 1. Yeah, it's just -1 over k. The series. So it's a series -1 over k. What do we know about that series? Sorry, what? Diverges. How do we know it diverges? It's a harmonics. It's the harmonic series times -1, right? So this is -1 times the harmonic series, and the harmonic series diverges. Remember, that -1 doesn't alternate, right? That just makes every term negative. So what is our conclusion there for that particular piece? Right. So since that resulted in a divergent series, when x is -1, sorry, let me say that again. Since x equals -1 results in a divergent series, we're not including that in the interval of convergence. It doesn't converge.
So leave that interval objective, right?
Right. So it's still as it is, nothing's changed. I'll just say here, just so we're clear, exclude x equal to -1 from, it's kind of redundant, the interval of convergence. It's kind of redundant to say that because it already is excluded, but when something diverges, we exclude. When it converges, we include. Okay. Yeah, so I don't know, let's see. So when x equals to 1, we have the series for -1 to the k plus 1 over k times x to the k.
That property just simplifies to
Times 1, yeah. Over k, right?
Over k.
So the 1 to the k is just 1. And so this series is -1 to the k plus 1 over k. What do we know about that series? Alternating harmonic. The alternating harmonic series converges, right? So this is an alternating harmonic.
Should we know how to prove that for the exam, or we just kind of say alternating harmonic convergence?
I would know both because honestly, you need to know the alternating series test.
Okay.
So as far as the harmonic and alternating harmonic are concerned, as is, it's okay to say that we know that they converge and diverge. So we've seen them a lot. Sorry, converges. Yeah, natural log of 2 converges too. And now I'll just also make a note here, if you forgot that, use the alternating series test. If you forgot. Okay, so then what do we do here? Yeah, you have to include x equal to 1 in the interval of convergence. Interval of convergence. Okay, so that's, does anyone need me to scroll up or down? Just say so if you do. And also, are there any questions?
The alternating series test, that's just non-increasing and ratio, or R is less than 1?
No, that's where, it's non-increasing, and typically what that translates to in practice is to show that it's decreasing. Okay, so yeah. And then the second condition is that for this one, the limit as k approaches infinity of 1 over k has to go to 0. Okay, so can I just go back up here and write this? The interval of convergence. The interval of convergence for the particular series found in part B is this. Or if you want to write it out as an inequality, -1 is less than x is less than or equal to 1.
Would that be the absolute value of x?
No, we're just because we know it's in this interval. If we said the absolute value, we would have those inequalities would have to be the same. Okay, so we start here to get that conclusion. And now if you look at that table, provided on page 5, you can see exactly where that comes from. 1, 2, 3, 4, 5. The 6th one down is the ln of x plus 1 or 1 plus x. We see the series representation, the terms written out, and we see for the -1 less than x less than or equal to 1. So we just justified that, which is why it's easier to remember these things and have to go through all of that every time you want to look at what series represents this particular function. And let's look at that as well. So here's our series in red, the function ln of 1 plus x. And remember, it's going to converge. The series is going to be the natural log of 1 plus x. As long as we're at 1 and less than, but also greater than -1. Let's see how that works out. So there's our linear approximation. You see, we're adding more and more terms, but not much is really happening. It's just that end piece there on the red end piece on the right is just kind of getting closer and closer here because this value is at -1. So +1. So if we can get there, we can see that this is our series. At that point, our series and the natural logarithm are the same. We're assuming again that this is an infinite series, right? So they're the same there. If we go out here to -1, we see that sort of dying off, approaching a vertical. So it's not converging here. Anybody have any questions about that example? Honestly, since we've referenced table 5, or sorry, table, I don't know what it's called actually. the table on page 5. 11.5, table 11.5. Except for this last one, we didn't talk about this last one. Let's just briefly mention a few things here, and then we'll take a break. The 1 over 1 minus x, you should know that because that's just the geometric series, which gives you 1 over 1 plus x when x is replaced with negative x. So this is just a substitution or a composition if you want to look at it like that. Our substitution x is negative x gives us the alternating geometric series. So those should be, it's like a 2-for-1 really, if you remember composition. E to the x, super important. Let me star these. E to the x. Notice sine x is an odd function. So sine consists of odd powers of x. They're all the odd powers that come from e to the x. If you remember e to the x and sine function's odd, just take the odd powers from the e function. Just don't forget to alternate them, because sine and cosine are both alternating series.
Is that x? K plus 1?
Yeah, for sine. Yeah, because we have 2k plus 1 is always odd. So we have all odd powers. 3, 5, 7, 9. Cosine is even, x to the 2k. 2k is always even. And again, these are the alternating sign or the alternating terms from e to the x. So if we split apart e to the x and alternate it, you've got sine and cosine from that. So really you get sine and cosine from e to the x, remembering that they alternate. Sine's odd, cosine's even. We just did this one. Look at inverse tangent. Does that inverse tangent look familiar? Yeah. Exactly. Inverse tangent, same as the sine, except for no factorial on the bottom.
Sine or?
Sine.
Oh, you're looking at.
So, with just remembering a few things, with e to the x, you get sine and cosine, and you get inverse tangent, basically. I don't know if that's helpful, but at least, hopefully, it doesn't make this look as overwhelming as it did when you first saw it. I don't know. That helps you out. Do you have any questions?
Oh, we gotta take a lot of derivatives. We take the example.
No. I'm trying to think, what's today? Now let's go back to our example number 3 that we skipped. We're kind of running short on time, so I want to just mention this here, that since a is equal to pi, the terms that you're coming up with there's our coefficient times, this time we'll have x minus pi, making that polynomial up. And so you want to find the first 4 non-zero terms. So we'll go through the same process we went through in the last example, and then write the power series. And I'll just write that out just in case you want to verify this or check that you do get the sum from k equals 0 to infinity, negative 1 to the k, times x minus pi to the 2k, cosine's an even function, over 2k factorial. So we're going to move on. Another thing we can do Yeah. I did want to mention this here, like when we looked at our graphs, like the 38th degree polynomial and the function itself, that's showing us that we do have an error or a remainder in our Taylor series, and so this just, you don't need to know this for the exam. I just wanted to mention it, that in order for the Taylor series to converge at or on that function, the error eventually, or the remainder eventually, has to go to 0. So I think we wrote this down, but we're saying that the function is the what do we call our Taylor polynomial piece of whatever, our Taylor polynomial plus the remainder. And so in order for the Taylor polynomial to actually equal the function as n approaches infinity, R of n must approach 0. But this theorem is telling us what, if we stop at like the 38th degree polynomial, what we can expect our error to be. It's not really precise because it says that the error stopping at the nth term, or the nth Taylor polynomial rather, is the next derivative. So we say we stopped at the 5th term and used a 5th degree Taylor polynomial. The error is the 6th derivative evaluated at some c over 6 factorial x minus a to the 6th. And that's what your error is. But it says for some c that's in between x and a. So for some c in between the variable, wherever you choose to stop it, and the center location. So that's really all I wanted to say there. With this table and was it theorem? This was theorem 11.4. These are old slides, but the theorem that told us how to combine power series with sum and differences, with multiplication and with composition. Those operations lend to the table. Was it 11.5? Or now, if we have all of these in terms of x, then we can just substitute various things, right? So if I have the series for cosine of x as this series here, then if I want to know the series for cosine of x cubed, I just put an x cubed in place of x. That's my composition. The cosine of x times x, then I multiply all of my terms by x. So we have many other representations from these series. For instance, use the Taylor series in the above table to find the first 4 non-zero terms of the series for ln of 1 plus x squared centered at 0. And from our previous example, we had that the ln of 1 plus, look at this, the ln of 1 plus x was the sum from 1 to infinity, negative 1 to the k plus 1 times x to the k over k. And then we'll write out the first 4 terms here was, it was x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So we did that example previous. And then to find the series for the ln of 1 plus x squared, we just replace that x with an x squared, and then we have that series. So the series for the ln of 1 plus x squared, it says just find the first 4 terms, so we don't really need the summation part. So x squared is the first term in for this x. And then we have x squared squared over 2. We have x to the 4th over 2. plus x squared cubed over 3 minus x squared to the 4th over 4. So they're the first 4 non-zero terms for that series, ln of 1 plus x squared. Does that make sense? We looked at a few examples in 11.2 like that, but that just kind of opens the door, those operations and this table, just opens the door to like many other series that we can represent.
So in the summation, we just replace x squared.
Right, yeah. Yeah, we would have this sum from k equals 1 to infinity, negative 1 to the k plus 1. Here, this x would be replaced by x squared, so we would actually have x squared to the k, or x to the 2 times k, right? All over k. Remember, the composition theorem tells us that this new series converges, same interval of convergence, as long as all of these powers are larger than 1, which they are because it's 2, 4, 6, 8. This function didn't ask us, but it actually, the function ln 1 plus x squared converges on the same interval that the ln of 1 plus x converges for.
Still be non-negative 1.
Right.
Would that be that also go with like x cubed?
Yeah. Yeah.
No power, doesn't matter what power x.
Yeah. So yeah, when we composition here, it says that when we plug this composition in here, our h of x is x squared. This converges to the composite function f of x squared, or ln of 1 plus x squared for all x, such that what we plugged in, x squared, is in that interval. So that let's think about this. So x squared has to be in this interval of convergence. So let's think about that, because that's gonna, I think the square is gonna affect this actually. So that's our interval of convergence for this here. And then so this converges, I might have misspoke. This converges for x squared in between 1, negative 1, including 1.
So yeah, it would include 1.
Yeah, excuse me, x squared actually though, x squared is always greater than negative 1, so really saying that here now doesn't make any sense. So when is x squared larger than or equal to 1? So we're thinking about x squared. When is it larger than, or sorry, less than or equal to 1? Well, it's equal to 1 at negative 1 and at 1, and then it's less than here. So it actually then comes in and includes negative 1. So it's from negative 1 to 1. On the but on the exam, if I ask you a question like this, and I will, I won't ask for the interval of convergence. I'll just ask you to represent the new series. I put it up here. Yeah, right.
So x cubed would be the same.
Yeah. Any other questions on that? So use the Taylor series in the table to find the first 4 non-zero terms of the function cosine root x. So this is where it's really helpful to remember the series for cosine. Otherwise, you've got to go through the process of, all right, what's the series for cosine? First, second, third, fourth, fifth, sixth derivative, evaluated at 0. Fit in the coefficients, write out the series. But if we can just remember that the cosine of x, again, it doesn't ask for the summation, so let's just write out the terms. The terms of cosine x are 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, 1, 2, 3, 4. Those are the first 4 terms for cosine. And then we just make the replacement x as the square root of x. does continue, but it's just the first 4. And then our square root goes in there. That's it. We can simplify, but that's virtually all we're doing here. So we've got 1 minus x over 2 factorial or 2. And we've got plus x squared over 4 factorial minus x cubed over 6 factorial. As the series for cosine root x. What values of the x does the series for cosine converge for? Cosine converges for all values. Yeah, cosine converges for all values. But will this converge for all values? Cosine root x? No, because you can't. Yeah, you can't plug in negative numbers. So that's convention is still the same. So I mean, we could plug negative. Notice we could plug negative numbers into the polynomial, right? But as far as using the negative numbers in the polynomial to say that's the cosine of like -4, and we would say that, or sorry, the root -4, cosine root -4 is 1 minus square root of -4 plus the square root of -4 squared, right? That doesn't make sense. So, anyways, that's all we were after, though. Anyone have any questions on that example?
You say all numbers for x, cosine of x, that's negative.
Yeah, for cosine of x, right? All real numbers. Similar example, inverse tangent of x squared times x. So here we're using a composition and a multiplication by the power. So if you didn't know this series for tangent x, again, it's a pretty lengthy process to come up with the series for tangent. So it's x minus x cubed over 3 plus x to the 5th over 5, say first 4, minus x to the 7 over 7. So here we have to compose with x squared and multiply by x. So we'll write out the inverse tangent of x squared is equal to x squared. X squared in for x, so that's x squared minus x to the 6th over 3 plus x to the 10th over 5 minus x to the 14th over 7.
What about that x?
Yeah, then we'll multiply all of that by x. So x times that series. We have x times x squared, x cubed. We see what happens here. So there's our series for x inverse tangent of x squared. Do y'all have any questions on any of that?
So if we wanted to use the table to figure out what the final one would look like, you would substitute your x squared in, your x there, but then you would also multiply that whole thing by x.
Right. Yeah, so you mean the actual series?
The series, yeah.
Yeah, so for inverse tangent was -1 x to the 2k plus 1 over 2k plus 1. Yeah, so we would substitute, we need to actually multiply by x as well. So we would then substitute that x squared. And then we'd have the power x 4k plus 2, right, if that were x squared.
Yeah.
4k plus 2 plus another 1.
plus another.
Yeah. Any other questions from 11.3? Okay, 11.4 is actually where we work with these, so it's kind of back to regular calculus. Once we know how to represent certain functions with power series, then we go back to sort of, there's a table again, regular calculus stuff. So really, I think I'll just, so we have time to talk about what's on the exam. I'll just mention a few things. I really want to focus on an example that's similar to what we would have on the exam, and then talk about the content of the exam. But a few things to mention here. This is a limit that evaluates to infinity over infinity. Honestly, the most efficient thing to do here is to apply L'Hopital's rule one time, and you get the answer to that limit. But the idea is that, okay, we've got a limit as x approaches 2. I'm going to take my function ln of 1 minus x, because, I mean, it's x minus 2. It's already a polynomial, right? We don't represent polynomials with infinite polynomials. It doesn't make sense. We're going to come up with a series for that. Center, where would we want to center that? At 0, at 2, what do y'all think? So since it's the limit as x is approaching 2, we want to know what that function looks like really close to 2, right? So we want to center this series at 2. Yeah, we'll see in the next example, not quite, but with finite numbers, yes. Okay, and again, just to save time, the series for the ln of x minus 1, again, you evaluate that at 2, derivative evaluated at 2, second derivative evaluated at 2, come up with the series for that term, or the terms for that series, rather. You come up with x minus 2 minus x minus 2 squared over 2 factorial plus 2 times x minus 2 cubed. Just got a few more terms over 3 factorial minus 6 times x minus 2 fourth over 4 factorial, and it keeps going. So, you know, infinite series representation for the logarithm x minus 1, that's going to go in for the function ln of x minus 1. So our limit as x approaches 2 on this function is now over all this stuff. So we're using the series for the function. I mean, it may seem kind of tedious. You want to verify through L'Hopital's rule that we get the same result. All of these terms have a factor of x minus 2 in common, so all of those terms, even the ones we didn't write out, we're factoring an x minus 2 out of, and then the x minus 2 divides with this x minus 2 up top. So then this is the limit as x approaches 2. 1, this is 1 minus x minus 2 to the first over 2 factorial plus 2 over 3 factorial times x minus 2 squared. We just diminished all of those subsequent terms by a power of x minus 2. So now as x approaches 2, what is our limit? just one, because everything with an x minus 2, which is this term, and all of these terms to the right, all of those things approach 0. So we end up with just 1 over 1 plus a bunch of zeros. So the limit is equal. So something like that.
So why is it 0?
Because x is approaching 2, and so it's just 0 over 2 factorial, 0 times 2 thirds, 2 over 6, etc. Because all of them have a power of x minus 2, which is 0, as x approaches 2. Any questions on that? Honestly, there's no limit on the exam. There is a couple in your homework though. So
this is the no test. No, this is no test.
not a limit, no. Example 2 sort of illustrates kind of, it's not necessarily a weak point in Taylor series, but it is where we have to sort of reformulate. So we're computing the limit at infinity. And the issue here is that it doesn't make sense to center a function at infinity. For that matter, you can't even center near infinity, right? Center around a finite number. So what should we do? Anybody have any ideas? So if we wanted to center this around 0, how would we go about doing that?
Our disappointment if we're not getting.
Well, it's good to think about it though. Yeah.
You have 1 over x sine and 1 over 1 minus x.
Yeah, so infinity over infinity takes on any value, right? It's indeterminate, so it could have any value. I'll give you a hint, it involves a substitution. So whatever you like. We're gonna say let u equal to, okay, 1 over x. Would that help us? If u equals 1 over x,
So you have x.
so x is going to infinity, so if we let u equal 1 over x, then what is u approaching? 0. It's actually 0 from the right because it's positive infinity. But does that help us? Why not?
We just be assigned a 0.
We have something that's approaching a finite number. Can we center about 0? Yeah, so the whole problem was the limit was at infinity. We can't center out at infinity. But as soon as we made this substitution, u is what we're going to work with. U is approaching 0. We can center at 0. Yeah, so as x approaches infinity on x sine 1 over x, in terms of u now, what is this? The limit as u approaches 0. What is x? u to the negative 1, 1 over u. We have 1 over u times the sine of u. So that was issue number 1. Now that we have this, we could, since we're working with series, L'Hopital's rule, we could use that and be done with it. Here now we're going to find a series representation for the sine of u, and then divide all terms by u. So just at least wanted to mention that. Now we find a series for sine of u. At the center of 0, because our limit is now approaching 0. Maybe you remember this special limit from Calc 1. It was involved in proving or justifying the derivative of sine and cosine. It was a pretty, I guess, special limit. But yeah, you should get that to come out to be 1. That limit is equal to 1. Have any questions? So remember, we can take a function representation, not only add, subtract, multiply, compose, but we can also integrate those things and differentiate those things. As a reminder from 11.2, we had that theorem in our notes that said when we differentiate or integrate, I don't know if y'all remember it, but it says either one of those operations, the radius of convergence is still the same. You don't affect the radius by differentiating or integrating, but you could affect the endpoints. So when you differentiate or integrate a power series, it's important to re-examine what happens at the endpoints, just like we did when we were doing like a root or a ratio test. So if we differentiate the series about 0, then again, that's why it's handy to know what is the series for the natural log of 1 plus x. Instead of having to compute all of the derivatives and find those, if we know what it is, we can just write it down. So what's the series? What's the series for the natural log of 1 plus x? So if we remember that, we can just use it. I don't know. Unless I specifically say find the Taylor series for this, like in a question like this, if you know this, then just write it down and then build off of that. So in part B, it says identify the function represented by the differentiated series. So here it's important, I think, to have the summation formula for that series.
What's the differentiator to x minus x squared? What is the differentiator?
Yeah, well, both, because they're the same thing, right? I think it's a little easier to see the derivative over here. But when we take the derivative of this, remember we're taking the derivative of all of that stuff with respect to x. So the only thing that gets differentiated is this x right here. It's x to the power of k. So the derivative of x to the power of k. Write this here. Just here. So when we take the derivative of that series, notice we're going to get the series for 1 over 1 plus x. That's the alternating harmonic, or the alternating geometric, rather. Derivative of x is 1. So, I think it's maybe a little easier to see here. 2 comes down, so we have 2x to the first over 2. So that's just x plus x squared minus x to the 4th. So that's our alternating geometric series. Notice the negative 1 to the k plus 1 is going to stay because that doesn't involve an x. We're differentiating with respect to x. So that negative 1 to the k plus 1 stays. Then this becomes k times x to the k minus 1 all over k. Just like if that were like to take the derivative of x to the 5th over 5 like we did on the far right.
Yeah, x to the 4 should be x to the 3rd.
Oh yeah. Thank you. Yeah, sorry about that. Yeah, and then the k's divide out. So let's be a little bit neater here. So notice that's not quite the representation for the alternating geometric series. I believe that's the second one in the formula on the first page. Their expression is negative 1 to the k times x to the k. So we're just, again, we've got x to the k minus 1. We would add 1 there, shift it over. And the index here doesn't, it does matter, but in the sense that we want to get these terms, 1 minus x plus x squared minus x cubed, etc., right? So they do have a slightly different representation from the table. It's just because we're going to shift this. We're going to add 1, so it's x to the k, which means we subtract 1 from the index. So we start at 0 here. But this is okay. I mean, it's the same thing that we started with. K equals 1. Gives us that series that we have.
Would that turn into k plus 2?
K plus 2.
Sorry, the negative 1. You should be in that.
No, so we want to add 1 here. We have to subtract 1 here. So it turns into 0 x to the k.
That wouldn't help you.
We have to shift the index here too, because if this were 0, then this is negative 1 to the 1. Gives us a negative 1 there.
Right.
So we want that to be just negative 1 to the k as well, which again, you see that reflected on the formula sheet. So here's what's listed on our formula sheet. They're the same series.
So if you go down on the, go add one?
Yeah. Yeah, so what you do to the expression, like add 1, you do the opposite, subtract 1 to the index summation.
To every k term.
Yes. Okay, so differentiating gives us new series as well. The interval of convergence for the ln of 1 plus x was from negative 1 to 1, including 1. But the deal with differentiating is now that we have to reevaluate our endpoints to see if they actually make this series converge. So, well, we've got to question this now. Okay, there's a question mark. Because that was the original interval of convergence for the ln of 1 plus x. Since we've taken the derivative, now we have to check these endpoints. Whichever series representation you want to use, it doesn't matter. They're all the same.
We tested, we don't want to use the k equals 1 infinity. We want to use
Yeah, I think this one's the one in blue is a little simpler, but it's totally up to you, whichever one you want to use, they're exactly the same.
Is that alternating geometric?
This one, yeah.
Does that make up bound?
Right, no, the original bounds for the interval of convergence were based off of this right here. So we start with that as like a baseline, and then we test the endpoints.
Why
Because we're
isn't
taking-
that k at k plus 2, where the arrow is pointing to -1?
Well, -1, so -1 to the k plus 2 is -1 to the k times -1 squared. And so -1 squared is always 1.
Is that portion is just alternating the series, so it really just matters if k is odd,
Yeah.
not the constant.
It really just matters, yeah, that's all that matters. Does it coincide with our signs here, plus minus, plus minus? All right. So when x equals to 1, we've got, I'm using this blue one, the series for -1 to the k times -1 to the k. And that's just 1 to the k, right? Does that converge or diverge? Divergence. Exclude -1 from the interval of convergence. Seems redundant because we already excluded it, but we could have very well had an inclusion here. We have to test to be sure. So we tested, and now we're sure. When x equals to 1. Yeah, 1 to the k is always 1, so yeah, it's 1 plus 1 plus 1 plus 1. So how about the series -1 to the k times 1 to the k? Does that converge or diverge? Yeah, how do you know it diverges? Right. What is the sum of that is either what or what? Or 1, yeah. So this series is equal to 0 or 1, depending on how many terms you add up, right? Since it's not a single finite number, it diverges. It can't converge to both 0 and 1. Do you have a question, Trey?
Yeah. It's like x equals -1. I've got 1.
Oh, so that's the same trick we used earlier. Since they're both to the kth power, it's just -1 times -1 to the k, which is positive 1 to the k, which is 1. So actually, we can't include 1 either. The original series included 1. The alternating geometric series doesn't include the endpoints. So, and you'll look at the table that matches the alternating geometric series converges for the absolute value of x less than 1. So the interval of convergence for the alternating geometric series is from -1 to 1, excluding the endpoints. That is, just like it says on the table, we write that with an absolute value. Same thing. Anyone have any questions on that? So just remember, when you apply the root or the ratio test to a power series, a function of x, you've got to test the endpoints. When you differentiate or integrate, you have to test the endpoints. Those are the two instances where you test the endpoints. Yeah, it's either 1 or -1, right? So depending on how many terms we add up, let's say we start at 1, we've got -1 plus 1 minus 1 plus 1 minus 1 forever. So we have 0 or 1 or -1, however you want to look at it, depending on how many terms you add up. Either way, it doesn't converge because you get two different values. It's kind of like it's oscillating, if you will, the sum is oscillating between two different values. It doesn't approach a single value.
We used to like, alternating conversions and.
Yeah, but that was with the alternating divided by k,
Right.
like the negative 1 over 1, negative 1 over 2, sorry, whatever that is. All right, and the example 4 is really the one of the main reasons or benefits of using Taylor series. So if you type this in like Desmos or a calculator that does compute this, then for sure it's using a Taylor series, because there is no known antiderivative for e to the x squared. Can't represent that as another function. We have to, in order to find the antiderivative of e to the x squared, we have to represent it as an infinite polynomial. So let's just remind ourselves or write out, what is the series for e to the x squared? So here, what are we looking for? We're taking the series and composing it, right? Yeah, x squared in for everything. So the series for e to the x is x to the n over n factorial. So it's going to be, or sorry, x to the k over k factorial. But we're not looking at the series for e to the x, we're looking at the series for e to the x squared. Does that make sense? You don't have any questions about that? It's super crucial. Of course, we could write this out as x to the power of 2k. Here we have always an even power over k factorial. And so we're going to say that e to the x squared is equal to, we'll just look at the terms of the series instead of the summation formula for it. When k is equal to 0, you could write out the series for e to the x as well and just replace x with x squared. However you want to do that, it's whether it's you.
I do have a quick question.
Yeah.
So when we're taking this off of the list for the Taylor series, why, when we do the x, we're starting at 0, but the last problem, we started at k.
Yeah, that was for the logarithm. So you got to be mindful, they all start at 0 except for the logarithm ones. Okay, so our first term is still 1. The x squared goes in for this x here. So we have 1 plus x squared. X squared goes in for this x squared, so x squared squared over 2 factorial. X cubed, sorry, x squared cubed over 3 factorial. Okay, so that is the series for e to the x squared. Notice the bounds of integration it's from 0 to 1, so we're pretty close to 0. That's why we're going to use the Maclaurin series. We're in that region from 0 to 1. Is everyone okay with where we're at? So in order to find the antiderivative from 0 to 1, or the integral from 0 to 1 of e to the x squared, we're just going to integrate with respect to x both sides of that equation. So the integral 0 to 1 with respect to x which is just equivalent to looking at this integration term by term. It's antiderivative of 1 with respect to x, antiderivative of x squared with respect to x, etc. Antiderivative of x to the 4 over 2 factorial. Yeah, 1 over 10. Right, so it's 1 over 5 times 2 factorial plus x to the 7th over 7 times 3 factorial plus x to the 9th over 9 times 4 factorial. And we can keep going, but I think that's just... Sorry.
Just evaluate that from 0 to 1.
Right, yeah, so there's our antiderivative. We're now going to evaluate this from 0 to 1. So notice when we plug in the lower bound fundamental theorem of calculus, everything is 0, right? So it ends up being really easy to evaluate. Now, typically what these problems say is we're never going to be able to get an exact value because we're using a finite polynomial. So typically what these questions will ask you is they'll say evaluate this and this integral with an error less than some specified value. Here we'll just do, we want to evaluate this to an error of less than 10 to the negative 2. Otherwise, it's really ambiguous as to what level of accuracy do we actually want, right? And really all that boils down to is looking for the term that's smaller than your error, right? If I add something that's like 1 over 10,000, it's not going to affect the second decimal place, is it? It's just going to affect the decimal place out here. So really we just need to look at, when we plug in our bounds, which term is actually less than our error, and we'll stop there. So by the fundamental theorem, we've got 1 plus 1 cubed over 3 plus 1 to the 5th over 10, or yeah, 1 to the 5th over 10 plus 1 to the 7th over 7 times 3 factorial plus 1 to the 9th over 9 times 4 factorial. That's 216. And then so on and so forth, right? There's our capital F of 1, and then we subtract off capital F of 0, which is 0. And our error, we want it less than 10 to the negative 2. So we just look at which one of these terms. Is 1 over 42 less than 10 to the negative 2? Well, it's 1 over, is 1 over 42 less than 1 over 100?
Oh, no.
Is 1 over 216 less than 100? Yeah, so we're going to stop here. This term is less than 10 to the negative 2. That's the first term that's less than our error, right? So we're going to stop there. Adding 1 over 216 to all of this other stuff isn't going to affect the second decimal place because it's less than 10 to the negative 2. So we're stopping here. And then what we're saying is then that the antiderivative, or the integral from 0 to 1 of e to the x squared with respect to x is approximately 1 plus a third plus a tenth plus a 42nd plus 1 over 216 within the specified error. Yeah, because it's less than this. If we stopped at 1 over 42, it's not less than the specified error. So we're affecting the decimal place before. The first term that's less than your error, right? I don't know if I computed that. 1.461. $772. From the series, and just for reference, the actual value, at least to more decimal places. 1.46, 265. And I just chose to stop there. We could get more levels of accuracy if we wanted to. So see, the error in our approximation lies in the third decimal place. Mm-hmm.
Yeah, like just ask you how many you wanna go out. For a major problem. 6?
Yeah, the alternating series.
Yeah, they'll tell you like which factors you wanna go out.
Yeah, yeah. So notice though, this isn't an alternating series. If this e to the x squared were represented by an alternating series, the error in any alternating series is at most the first neglected term. So like if we chose to stop at, we're stopping at the fifth term. If that were alternating, the error is at most this next term that we didn't write down. So we had examples in, or exercises in the alternating series section where it said, how many terms do we need to add up so that this error is less than 10 to the negative 4, whatever, right? So it all defaults back to that if it's an alternating series. Really, in practice, what it boils down to is just find the first term that's less than your given error and stop there. That's what it boils down to. Is everyone clear on that? Yeah. Sorry, that we didn't have time for review. I will, while y'all are filling out this, do y'all still want to do this? Can I let him stand and doing this? I will post the exam content on D2L, so make sure you're looking at that, as you study, so you can get a feel for what's important and what's not included.